Welcome to this deep dive on Azure Kubernetes Service in the banking domain. Today, we are going to explain Azure Kubernetes Service, commonly called AKS, from an end-to-end architecture point of view. We will look at why banks use it, how they host critical applications on it, how multi-tenant environments are designed, and how components like virtual networks, subnets, load balancers, storage accounts, deployments, stateful sets, cron jobs, Grafana, OpenTelemetry agents, and observability all fit together. Let us begin with the most important idea. Azure Kubernetes Service is not just a place to run containers. In a banking environment, AKS becomes a controlled application platform. It gives development teams a standard way to deploy applications, while giving central cloud, security, and operations teams a standard way to enforce governance, networking, monitoring, resilience, and compliance. A bank does not adopt AKS simply because Kubernetes is popular. A bank adopts AKS because the bank may have hundreds of applications across digital banking, payments, loan origination, customer onboarding, fraud detection, regulatory reporting, wealth management, and internal operations. Each application needs to move fast, but every application must also be secure, auditable, resilient, and compliant. That is the real promise of AKS in banking. It helps the organization create a shared, repeatable, secure platform for modern applications. Before we go into details, let us build a simple mental picture. At the bottom, we have Azure infrastructure. This includes Azure subscriptions, resource groups, virtual networks, subnets, route tables, Azure firewall, network security groups, private endpoints, managed identities, key vault, storage accounts, databases, monitoring services, and policy controls. Above that, we have AKS. Azure manages the Kubernetes control plane, while the bank manages the worker nodes, node pools, networking design, security configuration, workload placement, and operational standards. Above AKS, we have application workloads. These workloads may be web applications, application programming interfaces, background processes, scheduled jobs, event processes, reporting services, integration services, or data processing components. Above the applications, we have banking channels. These include mobile banking, internet banking, branch applications, call center tools, partner interfaces, merchant systems, automated telemachine integration, and internal staff portals. When a customer checks an account balance, applies for a loan, confirms a payment, uploads a document, or updates a profile, the request may pass through multiple layers. It may enter through a global edge service, pass through an application gateway or application programming interface gateway, reach microservices running inside AKS, call a database, publish an event, generate logs, emit traces, and return a response to the customer. The customer sees one simple action. Behind the scenes, the architecture is carefully designed. Now let us talk about the banking use case more practically. Imagine a bank building a digital onboarding platform. A customer opens the mobile application and starts an account opening journey. The customer submits personal details, uploads identity documents, completes verification, and receives an approval response. In a traditional architecture, this journey might be hosted across virtual machines, manual deployments, shared file systems, and separate monitoring tools. Scaling might be slow. Deployments might require maintenance windows. Troubleshooting might take a long time. In an AKS-based architecture, the same journey can be broken into microservices. There may be a customer profile service, document upload service, identity verification service, risk scoring service, notification service, workflow orchestration service, and audit logging service. Each service runs as a container. Each service can scale independently. Each service can be deployed independently. Each service can have its own resource limits, security controls, health checks, and observability signals. This is why AKS is valuable. It lets a bank treat application hosting as a platform capability rather than a collection of individual servers. Now let us examine the major architecture layers one by one. The first layer is subscription and landing zone design. In banking, workloads are usually not placed randomly into a single Azure subscription. Banks normally use a landing zone architecture. A landing zone is a prepared cloud environment with networking, identity, policy, logging, security controls, and governance already in place. A common pattern is to have a management subscription for shared management capabilities, a connectivity subscription for hub networking and firewall services, identity services connected to Microsoft Entra ID, and separate workload subscriptions for application environments. For AKS, this means a bank might have separate subscriptions for development, testing, user acceptance testing, production, and highly regulated workloads. Some banks also separate business domains. Retail banking might use one subscription group, payment processing another, lending another, and analytics another. This separation matters because banking workloads have different risk profiles. A customer-facing payment workload has different controls compared with an internal reporting dashboard. A fraud analytics platform has different data sensitivity compared with a marketing content service. Subscription boundaries help with security, cost management, role separation, audit, and operational ownership. The second layer is virtual network design. A virtual network, or VNet, is the private network boundary where Azure resources communicate. In an AKS architecture, the VNet is one of the most important design decisions. For banks, AKS is usually deployed into a private network. This means the cluster is not casually open to the internet. Application traffic enters through controlled paths, and management traffic is restricted. The VNet is often divided into subnets. One subnet may be used for AKS nodes. Another subnet may be used for application gateways. Another subnet may be used for private endpoints. Another subnet may be used for firewall or network virtual appliances. Some designs also separate system node pools and user node pools by subnet, especially when stronger traffic control is required. A subnet is not just an address range. In enterprise architecture, a subnet becomes a control zone. Route tables can be associated with it. Network security groups can be applied. Private endpoints can be placed into it. Traffic can be directed through firewall inspection. The subnet becomes part of the security boundary. For example, a bank may decide that all outbound traffic from AKS must go through Azure Firewall. This prevents workloads from making uncontrolled internet calls. If a payment service needs to call an external payment network, that path can be explicitly approved and monitored. If a document verification service needs to call an approved partner endpoint, that traffic can be routed and logged. Unknown outbound traffic can be blocked. This is especially important in a multi-tenant AKS platform, where many application teams share the same cluster or shared platform. The network must prevent accidental or unauthorized communication between workloads. The third layer is AKS cluster design. An AKS cluster has a managed control plane and worker nodes. The control plane includes Kubernetes components that manage scheduling, state, and cluster behavior. Azure manages that control plane for AKS. The bank operates the worker nodes where application containers run. In production banking environments, clusters are usually designed for high availability. Nodes are spread across availability zones where available. Multiple node pools are used to separate workload types. A system node pool is used for critical platform components. These may include core Kubernetes services, networking components, monitoring agents, service mesh components, and other platform-level pods. User node pools are used for application workloads. A bank may create separate user node pools for web applications, background processing, high memory workloads, batch workloads, and regulated workloads. This separation helps with scaling, cost, performance, and isolation. A heavy batch job should not affect a customer-facing mobile banking service. A memory-intensive fraud model should not compete with lightweight application programming interface services. A development workload should not run on the same node pool as a production payment workload. Node pools also support cost optimization. Critical workloads may run on standard reliable virtual machine sizes. Non-critical batch workloads may run on lower-cost node pools. Development clusters may use auto-scaling and scheduled scaling patterns to reduce cost outside working hours. Now let us focus on multi-tenant design. Multi-tenancy means that multiple application teams, business units, or workload owners share the AKS platform. In banks, this is very common because a central platform team wants to provide a standard Kubernetes platform to many teams. There are three common multi-tenant models. The first model is namespace-based multi-tenancy. In this model, one AKS cluster is shared by multiple teams. Each team gets one or more Kubernetes namespaces. A namespace is a logical boundary inside Kubernetes. Role-based access control limits what each team can do. Resource quotas prevent one team from consuming too much capacity. Network policies restrict communication between namespaces. Policy controls prevent risky configurations. For example, the loan origination team may have its namespace. The customer notification team may have another namespace. The document processing team may have another. Each team deploys its own services, but platform controls remain consistent. This model is efficient and cost-effective. It is useful for non-production environments and for workloads with similar risk levels. However, it requires strong governance. If namespace boundaries are weak, teams can accidentally affect each other. The second model is cluster-based isolation. In this model, each major workload or business domain gets its own AKS cluster. Payment processing may have a dedicated cluster. Fraud detection may have another. Digital banking may have another. This provides stronger isolation, but increases operational overhead and cost. The third model is hybrid. This is often the most realistic banking model. Shared internal services and lower-risk workloads may use shared clusters. Critical workloads, regulated workloads, or workloads with special network requirements may use dedicated clusters. This is where architecture judgment matters. If every workload gets a separate cluster, the bank may create too much complexity. If every workload shares one cluster, the bank may create too much risk. The platform team must classify workloads and select the right tenancy model. Now let us discuss load balancing. Load balancing is how traffic is distributed across running application instances. In AKS, a service can expose application pods through a Kubernetes service. When the service type is load balancer, Azure can create an Azure load balancer that sends traffic to the correct nodes and pods. Azure Load Balancer operates at Layer 4. That means it works mainly with transport-level traffic such as Transmission Control Protocol and User Datagram Protocol. It does not understand application routes like a Layer 7 gateway does. For simple traffic distribution, it is excellent. In banking, there are two major load balancer patterns. The first is public load balancing. This exposes an application through a public endpoint. Banks use this carefully, usually only at controlled entry points. For internet-facing banking workloads, traffic normally comes first through edge protection, web application firewall, and application routing services before reaching back-end services. The second is internal load balancing. This exposes services using private IP addresses inside the VNet. This is very common in banking. An internal load balancer allows one internal system to reach another without exposing it to the public internet. For example, an internal account validation service running in AKS may be exposed through an internal load balancer. Other systems inside the bank network can call it through private networking. It does not need a public Internet Protocol address. In a mature AKS design, load balancing is not the only entry control. Banks often use ingress controllers or application gateways for Layer 7 routing. Layer 7 routing can make decisions based on host names and paths. For example, traffic for customer onboarding can be routed to one service, while traffic for payments can be routed to another service. An ingress controller sits inside or near the AKS cluster and routes incoming application traffic to services inside the cluster. Azure Application Gateway can also integrate with AKS, providing web application firewall capabilities and application-aware routing. Some banks use Azure Front Door at the global edge, then Application Gateway in the regional network, then AKS services behind that. So the flow may look like this in words. A customer request reaches the global edge. The request is inspected and routed by a web application firewall. It enters a private regional application gateway. The gateway forwards the request to an ingress controller or directly to a Kubernetes service. The service distributes traffic across pods. The pods process the request and call downstream services. This layered approach protects the application and gives the bank multiple control points. Now let us talk about private clusters. In many banking scenarios, the AKS control plane endpoint is private. That means the Kubernetes application programming interface server is not publicly reachable. Administrators and pipelines connect through secured private network paths. This reduces the attack surface. A private AKS cluster fits well with hub and spoke networking. The hub contains shared security and connectivity services such as firewall, domain name resolution, and monitoring. The AKS cluster runs in a spoke VNet. Traffic between the hub and spokes is controlled through peering and routing. Private clusters require careful planning for domain name resolution. If the cluster control plane uses private endpoints, internal systems such as deployment agents, jump hosts, or continuous delivery tools must be able to resolve private domain names and reach the private endpoint. This is why networking, domain name system configuration, and DevOps architecture must be designed together. Now let us discuss deployment patterns. In Kubernetes, a deployment is used for stateless applications. Stateless means the application does not store important local data inside the container. If a pod is deleted and recreated, the application should still function because its state is stored outside the pod, such as in a database, cache, message queue, or storage service. Most banking microservices should be designed as stateless where possible. A balance inquiry service, customer profile service, notification service, or payment validation application programming interface can often be stateless. Kubernetes can then scale the service by adding more pods. If one pod fails, another pod can replace it. Deployments support rolling updates. This means a new version can be deployed gradually, while the old version continues serving traffic. If something goes wrong, the deployment can be rolled back. In a banking environment, this supports controlled change management and reduces downtime. A replica set works behind the scenes to maintain the desired number of pod replicas. If the desired replica count is 4, Kubernetes tries to keep 4 pods running. If one fails, it starts another. Horizontal pod autoscaling can increase or decrease the number of pods based on metrics such as central processing unit usage, memory usage, or custom application metrics. For example, if mobile banking traffic increases during salary credit days, the platform can scale out customer-facing services. When demand decreases, it can scale back. Now let us talk about stateful sets. A stateful set is used when application instances need stable identities, stable network names, or stable storage. In general, banks prefer managed data services for critical databases, such as Azure SQL Database, Azure Database for PostgreSQL, Azure Cosmos DB, or other managed services. These services provide mature backup, high availability, maintenance, and security capabilities. However, there are cases where stateful sets are relevant. Some distributed systems, messaging platforms, data processing tools, or specialized applications may need stable pod identities. A stateful set gives each pod a predictable identity. For example, pod 0, pod 1, and pod 2 are not interchangeable in the same way as stateless pods. Stateful sets often use persistent volumes. A persistent volume allows data to survive even when a pod is restarted. In Azure, persistent volumes may use Azure Disk or Azure Files depending on access pattern. Azure Disk is commonly used when one pod needs mounted block storage. Azure Files is useful when multiple pods need shared file access. In banking architecture, stateful sets must be treated carefully. They bring more operational responsibility. Backups, restore testing, encryption, performance, availability zones, disaster recovery, access control, and upgrade strategy all become important. If a managed service can solve the requirement better, the managed service is often preferred. If stateful sets are used, they should follow strict platform standards. Now let us discuss cron jobs. A Kubernetes cron job runs a task on a schedule. In banking, scheduled tasks are common. A cron job might perform daily reconciliation, generate a regulatory report extract, clean temporary files, refresh a reference data cache, send end-of-day notifications, or trigger a batch workflow. For example, a bank may need an end-of-day account summary process. A cron job can start a container at a scheduled time. The container reads required data, performs processing, writes results, sends events, and exits. Kubernetes tracks the job status. Cron jobs are useful, but they require discipline. The platform must define concurrency rules. What happens if yesterday's job is still running when today's job starts? Should the second job be blocked, allowed, or replace the earlier one? The design must also define retry behavior, failure handling, logging, alerting, and idempotency. Idempotency means the job can safely run more than once without corrupting data. In banking, this is very important. If a scheduled reconciliation job runs twice, it must not duplicate financial transactions. If a notification job retries, it must not send duplicate messages unless that behavior is intended and controlled. Now let us talk about storage accounts. An Azure storage account is a foundational service for storing objects, files, queues, and tables. In AKS architecture, storage accounts can appear in several ways. First, applications may store documents or files in blob storage. A digital onboarding application may store uploaded documents in a controlled storage account. A statement service may store generated statements. A reporting service may produce output files. Second, applications may use Azure Files for shared file scenarios. Some legacy or commercial applications expect a file share. Azure Files can provide a managed file share that containers mount. Third, storage accounts may be used for logs, exports, backups, temporary files, or integration with downstream systems. In banking, storage account design is security sensitive. Storage should be private by default. Public access should be disabled unless there is a very specific controlled requirement. Private endpoints should be used so that AKS workloads access storage over private network paths. Data should be encrypted. Access should use managed identity wherever possible instead of embedded secrets. Role-based access control should be applied. Sensitive containers should have lifecycle policies, immutability where required, retention controls, and audit logging. A common mistake is treating storage accounts as simple file buckets. In a bank, a storage account is often a regulated data location. The architecture must define what data is stored, who can access it, how long it is retained, how it is encrypted, how it is backed up, and how access is monitored. Now let us discuss secrets and identity. Containers should not contain passwords, connection strings, or private keys inside images. In banking, this is a strict principle. Secrets should be stored in Azure Key Vault. Workloads should use managed identities to access Key Vault or other Azure services. Managed identity allows an application to authenticate to Azure resources without storing credentials. This is powerful in AKS because pods can be given workload identities. Instead of putting a storage account key in a configuration file, a pod can use its identity to request access to a storage account, key vault, or database. This improves security and operations. If a workload no longer needs access, the identity permission can be removed. If an application moves between environments, it can use environment-specific identities and policies. Access can be audited. For human access, Microsoft Entra ID integrates with Kubernetes role-based access control. Platform engineers, developers, support engineers, and auditors can receive different permissions. A developer may deploy only to a development namespace. A production support engineer may view logs, but not modify secrets. A platform administrator may manage cluster-level components. This supports separation of duties. Now let us talk about observability. Observability is not the same as monitoring. Monitoring tells you whether something is wrong. Observability helps you understand why it is wrong. In AKS, observability usually includes metrics, logs, traces, events, and alerts. Metrics are numerical measurements. Examples include central processing unit usage, memory usage, pod restart count, request rate, error rate, response time, queue depth, and database connection count. Logs are records of events. Application logs explain what the application did. Container logs show output from pods. Platform logs show cluster-level behavior. Audit logs show who changed what. Traces follow a request across multiple services. In microservices, this is critical. A single payment request may call the authentication service, customer service, payment validation service, fraud scoring service, ledger adapter, notification service, and audit service. If the request is slow, traces help identify which service caused the delay. Events show changes such as pod scheduling failures, image pool errors, node pressure, failed health checks, or scaling actions. For AKS, Azure Monitor can collect metrics and logs. Container Insights can show cluster and workload health. Managed Prometheus can collect Kubernetes and application metrics. Azure Managed Grafana can visualize metrics in dashboards. Together, these tools provide a strong observability foundation. Now let us bring Grafana into the picture. Grafana is a visualization platform. In banking, platform teams use Grafana dashboards to show the health of clusters, namespaces, applications, node pools, and business services. A platform dashboard might show total nodes, unavailable nodes, pod restarts, namespace resource usage, cluster autoscaler activity, storage volume status, ingress error rates, and network traffic. An application dashboard might show request count, latency percentiles, error rate, dependency failures, queue backlog, and business transaction status. A banking operations dashboard might show payment service health, onboarding journey success rate, document processing backlog, fraud scoring response time, and scheduled job completion. Grafana becomes the shared language between platform engineers, application teams, and operations teams. Instead of everyone looking at separate tools, the organization can create standard dashboards. Now let us talk about the OpenTelemetry agent. OpenTelemetry is an open standard for collecting telemetry such as traces, metrics, and logs. In AKS, an OpenTelemetry collector or agent can be deployed to collect telemetry from applications and forward it to observability backends. There are different deployment patterns. An agent can run as a daemon set, which means one pod runs on each node. This is useful for collecting node local telemetry. A collector can also run as a central deployment, where application telemetry is sent to collector pods that then forward data to Azure Monitor, Prometheus, Grafana-related systems, or another observability platform. In a banking platform, OpenTelemetry helps standardize observability across teams. Instead of every team inventing its own logging and tracing format, the platform provides common instrumentation patterns. Applications emit traces with correlation identifiers. Logs include request identifiers. Metrics use agreed naming conventions. Dashboards become easier to build. Consider a failed payment transaction. Without tracing, the support team may only know that the customer saw an error. With distributed tracing, the team can see that the mobile request reached the ingress, passed authentication, called payment validation, waited too long for fraud scoring, retried, and finally failed because a downstream dependency timed out. That is a completely different level of operational insight. This is why observability is not optional in banking AKS. It is a core architecture capability. Now let us discuss health probes. Kubernetes uses probes to understand application health. A readiness probe tells Kubernetes whether a pod is ready to receive traffic. A liveness probe tells Kubernetes whether a pod should be restarted. A startup probe helps applications that need more time to start. For banking applications, probes must be designed thoughtfully. A readiness check should confirm that the application can actually serve requests. If a service depends on a database, cache, or configuration system, the readiness design must reflect real readiness without creating unnecessary cascading failures. A bad health check can cause outages. If the liveness probe is too aggressive, Kubernetes may restart healthy pods during temporary slowness. If the readiness probe is too weak, traffic may be sent to pods that cannot process requests. Health probes are small configuration details with large operational impact. Now let us move to deployment pipelines. Banks rarely allow direct manual deployment to production. A typical deployment flow starts with source code. The application team commits code. The continuous integration system builds the container image. Security scans check the image for vulnerabilities. Static analysis checks code quality. Unit and integration tests run. The image is pushed to a container registry. Deployment manifests or Helm charts are validated. Policy checks confirm that the workload meets platform rules. Then the release pipeline deploys to AKS. For production, approvals may be required. Some banks use progressive delivery. This means gradually shifting traffic to a new version. Canary deployments release a new version to a small percentage of traffic first. Blue-green deployments run two versions side by side and switch traffic when the new version is approved. Rolling deployment replaces pods gradually. In customer-facing banking systems, progressive delivery reduces risk. If the new version creates errors, traffic can be shifted back, or the deployment can be rolled back quickly. Infrastructure as code is also important. AKS clusters, node pools, networking, role assignments, policy definitions, monitoring settings, and private endpoints should be defined as code. This gives repeatability. It also supports auditability, because changes are reviewed and tracked. Now let us discuss policy and governance. Kubernetes gives teams a lot of power. Without governance, that power can create risk. A developer might run a privileged container. A workload might run as root. A pod might request too much memory. An application might expose a public endpoint. A container image might come from an unapproved registry. Secrets might be placed directly inside manifests. In banking, these risks must be controlled with policy. Azure policy for Kubernetes and admission controls can enforce rules. For example, workloads must use approved container registries. Containers must not run privileged. Resource requests and limits must be defined. Public load balancers may be blocked in restricted namespaces. Required labels must be present for cost allocation and ownership. Images must pass security scanning before deployment. Only allowed storage classes may be used. Policy turns platform standards into enforceable controls. It also helps teams move faster. Instead of every design requiring manual review, the platform encodes guardrails. Teams can deploy freely inside safe boundaries. Now let us look at security from end to end. Security begins before a request reaches AKS. At the edge, traffic may be protected by distributed denial of service protection, web application firewall rules, and global routing. At the network layer, traffic passes through controlled entry points, private networking, route tables, and firewalls. At the identity layer, users and workloads authenticate through Microsoft Entra ID and managed identities. At the application layer, services validate tokens, enforce authorization, and protect sensitive data. At the platform layer, Kubernetes role-based access control, network policies, pod security standards, and image controls protect the cluster. Network policies are especially important in multi-tenant environments. By default, teams should not assume that every pod can talk to every other pod. A customer onboarding service may need to call a document service. It may not need to call a payment reconciliation service. A reporting job may need database access. It may not need internet egress. Network policies express these rules inside Kubernetes. Secret management is also central. As mentioned earlier, secrets should be stored in Key Vault. Applications should use managed identities. Secrets should be rotated. Access should be audited. Container security is another layer. Images should come from approved registries. Base images should be maintained. Vulnerability scans should run in the pipeline and continuously after deployment. Runtime protection should detect suspicious behavior. In banking, security architecture is layered because no single control is enough. The goal is defense in depth. Now let us discuss reliability. A banking service must be resilient because customers expect availability. AKS supports reliability through multiple mechanisms. At the pod level, multiple replicas can run across nodes. At the node level, node pools can scale and recover. At the zone level, nodes can be distributed across availability zones. At the cluster level, production clusters can be designed with separate system and user node pools. At the regional level, critical banking applications may use active-active or active-passive architectures across Azure regions. Pod disruption budgets help maintain availability during maintenance. A pod disruption budget tells Kubernetes how many pods must remain available when voluntary disruptions occur. For example, if a service has 6 replicas, a disruption budget may require at least 5 to remain available during node upgrades. Cluster autoscaler helps add nodes when the cluster needs more capacity. Horizontal pod autoscaler helps add pods when workload demand increases. Together, they help the platform respond to changes in traffic. However, scaling must be tested. If a payment service needs to scale quickly during peak hours, the architecture must confirm that container startup time, image pool time, node provisioning time, database connection limits, and downstream service limits can support that requirement. Scaling the pods alone is not enough if the database cannot handle more connections. Now let us talk about disaster recovery. For stateless AKS applications, disaster recovery focuses on redeploying applications and routing traffic to a healthy region. For stateful components, disaster recovery is more complex. Databases, storage accounts, message brokers, and persistent volumes need backup, replication, and restore strategies. In banking, disaster recovery requirements are usually defined by recovery time objective and recovery point objective. Recovery time objective means how quickly the service must be restored. Recovery point objective means how much data loss is acceptable. For critical banking workloads, these objectives may be strict. The architecture may use multi-region deployment, replicated databases, geo-redundant storage, traffic manager, or global routing, automated infrastructure deployment, and tested runbooks. The key word is tested. A disaster recovery plan that is never tested is only a document. Banks need regular exercises to confirm that clusters, applications, data, secrets, identities, networking, and monitoring can be recovered. Now let us discuss cost management. AKS can be cost-efficient, but only if it is designed and operated properly. Cost drivers include node size, number of nodes, persistent storage, log volume, monitoring data, network egress, load balancers, public IP addresses, private endpoints, container registry, and backup storage. A common cost issue is over-requested resources. If every application requests more central processing unit and memory than it needs, the cluster will require more nodes. Resource requests and limits should be based on measurement. Teams should review actual usage and tune requests. Another cost issue is excessive logging. Observability is important, but uncontrolled log volume can become expensive. Banking platforms should define log levels, retention policies, sampling strategies, and data routing. Not every debug log belongs in long-term storage. Node pool design also affects cost. Critical workloads may need premium nodes. Batch workloads may run on separate lower-cost pools. Non-production clusters can scale down when not needed. Environments should be tagged for cost allocation so teams understand consumption. Now let us walk through a reference banking architecture. Imagine a bank running a digital banking platform on AKS. The customer uses a mobile application. The request reaches a global edge service. Web application firewall rules inspect the request. Valid traffic is routed to a regional application gateway. The application gateway forwards traffic through private networking to services hosted in AKS. Inside AKS, the ingress layer routes traffic to microservices. The authentication service validates the user token. The profile service retrieves customer details. The account service retrieves account summaries from a managed database or core banking integration layer. The transaction service retrieves recent transactions. The notification service sends alerts. The audit service records activity. Some services communicate synchronously through internal application programming interfaces. Others communicate asynchronously using a message broker or event streaming service. For example, when a customer updates contact details, the main service may publish an event. Downstream services update caches, send notifications, and write audit records without slowing down the customer request. Data is stored in managed databases and storage accounts. Identity documents or generated files are stored in private blob storage. Secrets are stored in Key Vault. Workloads access resources using managed identities. Observability is built in. Applications emit logs, metrics, and traces. OpenTelemetry collectors gather telemetry. Prometheus collects metrics. Grafana displays dashboards. Azure Monitor stores logs and raises alerts. Security events flow to security monitoring platforms. Operations teams can see whether the digital banking platform is healthy. Application teams can troubleshoot their own services. Security teams can audit access. Platform teams can manage capacity and upgrades. Now let us discuss how different banks may choose different hosting patterns. A large retail bank with many product teams may use shared AKS clusters for non-production environments and dedicated clusters for production domains. This balances cost and isolation. A digital-only bank may use a more platform-native design, with strong automation, GITOps deployments, service mesh, managed observability, and frequent releases. The architecture may emphasize speed, elasticity, and controlled experimentation. An investment bank may run analytics and risk workloads on separate node pools or separate clusters, because workloads may be compute-intensive and data-sensitive. Batch jobs, model scoring, and data pipelines may need different scaling and storage patterns. A payments-focused institution may choose strong isolation for payment workloads, strict network egress control, dedicated clusters, private endpoints, high availability zones, and carefully tested disaster recovery. A bank modernizing legacy systems may use AKS as an integration layer. The core banking system may remain on existing platforms, while new digital services run on AKS and communicate through secure application programming interfaces, message queues, and controlled adapters. The specific architecture differs, but the principles remain consistent. Secure networking, identity-based access, strong isolation, automated deployment, observability, resilience, governance, and cost control. Now let us talk about operating model. A successful AKS platform in banking needs clear ownership. The platform team owns the cluster foundation. This includes cluster provisioning, node pools, networking, ingress standards, storage classes, policy controls, monitoring baseline, upgrade process, backup integration, identity integration, and platform documentation. The security team owns security standards, threat detection, vulnerability policies, access review, compliance controls, and audit requirements. The application teams own application code, container images, deployment manifests, application configuration, business logic, tests, and service-level objectives. The operations team owns incident response, alert handling, runbooks, service health, and coordination during production issues. The architecture team ensures that the overall design aligns with enterprise principles, regulatory expectations, resilience requirements, and cost standards. Without this operating model, AKS can become chaotic. With the right operating model, AKS becomes a powerful internal platform. Now let us discuss service mesh briefly. Some banks use a service mesh to manage service-to-service communication. A service mesh can provide mutual transport layer security, traffic shifting, retries, timeouts, circuit breaking, and detailed telemetry. It can help standardize communication between microservices. However, service mesh also adds complexity. It introduces sidecars or managed data plane components, additional configuration, and operational overhead. Banks should adopt service mesh when they have a clear need, such as strong service identity, advanced traffic control, or deep east-west observability. It should not be added just because it is fashionable. Now let us discuss storage classes and persistent volumes. In Kubernetes, a storage class defines how storage is dynamically created. For AKS, storage classes may map to Azure Disk or Azure Files. When an application requests storage through a persistent volume claim, Kubernetes uses the storage class to create or attach the right storage. For example, a document processing workload may mount temporary shared storage. A specialized stateful application may request a managed disk. A reporting service may write output to a file share before moving it to a storage account. The platform team should define approved storage classes. These should include encryption settings, performance tiers, reclaim policies, and allowed usage patterns. In banking, teams should not create arbitrary unmanaged storage patterns. Now let us talk about image registries. Containers are built into images and stored in a registry. Azure Container Registry is commonly used with AKS. The registry should be private. Access should be controlled through managed identity or role assignments. Images should be scanned. Old images should be cleaned up. Critical base images should be maintained and patched. A secure image supply chain is essential. The bank must know what is running, where it came from, who built it, whether it passed security checks, and whether it is approved for production. Now let us connect all this with an example deployment. A team builds a new fraud scoring service. The service receives transaction context and returns a risk score. Developers write the code and create a container image. The pipeline runs tests and security scans. The image is pushed to a private container registry. The deployment manifest defines a Kubernetes deployment with 3 replicas, resource requests and limits, readiness and liveness probes, and environment configuration. The service is exposed internally because only other banking services should call it. The workload uses managed identity to retrieve configuration from Key Vault and to access approved data services. Network policies allow calls only from payment validation services and block unrelated namespaces. Metrics and traces are emitted through OpenTelemetry. Grafana dashboards show latency, error rate, and risk scoring volume. Alerts notify the support team if response time exceeds the service level objective. If transaction volume increases, the horizontal pod autoscaler adds more replicas. If the cluster lacks capacity, the cluster autoscaler adds nodes. If a new version is released, a canary deployment sends a small portion of traffic to the new version first. If the new version behaves correctly, traffic gradually increases. If errors rise, the release is stopped or rolled back. This is a practical AKS operating model in a banking context. Now let us discuss common mistakes. The first mistake is treating AKS like a simple hosting environment. Kubernetes is powerful, but it requires standards. Without platform engineering, every team creates its own pattern. The second mistake is weak network design. If subnets, private endpoints, firewall rules, and domain name resolution are not planned properly, the platform becomes fragile. The third mistake is poor observability. If applications do not emit useful logs, metrics, and traces, production incidents become slow and painful. The fourth mistake is ignoring resource management. Without requests, limits, quotas, and autoscaling, one workload can affect others. The fifth mistake is using Kubernetes for stateful systems without operational maturity. Stateful workloads need backup, restore, performance, and recovery planning. The sixth mistake is allowing too many exceptions. Banking platforms need flexibility, but uncontrolled exceptions weaken security and increase support cost. Now let us summarize the end-to-end AKS banking architecture. Start with a governed Azure landing zone. Use subscriptions and resource groups to separate environments and business domains. Design hub and spoke networking. Place AKS in private VNets. Use subnets as control boundaries. Route traffic through approved ingress, firewall, and private endpoints. Use internal load balancers for private services and application gateways for application-aware routing. Design AKS clusters with separate system and user node pools. Use namespace-based multi-tenancy where appropriate, cluster-based isolation where necessary, and a hybrid model for enterprise scale. Apply role-based access control, policy controls, resource quotas, network policies, and secure image standards. Use deployments for stateless microservices. Use stateful sets only when stable identity and persistent storage are truly needed. Use cron jobs for scheduled workloads like reconciliation, reporting, cleanup, and batch processing. Use storage accounts for documents, exports, integration files, and controlled object storage. Protect storage with private endpoints, encryption, managed identity, and audit logging. Use Azure Monitor, Prometheus, Grafana, and OpenTelemetry to create full observability. Capture metrics, logs, traces, and events. Build dashboards for platform health, application health, and business service health. Define alerts that are meaningful and actionable. Use automated deployment pipelines. Build container images securely. Scan them. Store them in private registries. Deploy using controlled release strategies. Use infrastructure as code and policy as code. Test disaster recovery. Review cost. Continuously improve. The most important lesson is that AKS in banking is not only a technology decision. It is an architecture decision, a security decision, an operations decision, and a governance decision. Azure Kubernetes Service gives banks a way to modernize application hosting. It supports microservices, automation, scaling, and resilience. But the real value comes when AKS is wrapped with the right platform capabilities. A well-designed AKS platform allows teams to innovate quickly without bypassing controls. It allows security teams to enforce standards without blocking delivery. It allows operations teams to observe and recover systems. It allows architects to design reusable patterns. It allows the bank to support digital transformation while respecting regulatory expectations. If you are explaining AKS to a banking audience, do not start with pods and YAML. Start with the business problem. Banks need secure, scalable, resilient, auditable platforms for modern applications. Then explain the architecture. Azure provides the landing zone, network, identity, storage, monitoring, and security services. AKS provides the Kubernetes execution platform. Application teams bring their containers and business logic. Platform teams provide the guardrails. Operations teams keep the system reliable. Then move into the components. Load balancers control traffic distribution. VNets and subnets define private network boundaries. Ingress and application gateways manage application traffic. Storage accounts store files and objects securely. Deployments run stateless services. Stateful sets run workloads that need stable identity and storage. Cron jobs run scheduled tasks. Grafana shows dashboards. OpenTelemetry standardizes telemetry. Azure Monitor collects and alerts. Policies enforce standards. Managed identities remove secrets from applications. When these pieces work together, AKS becomes much more than a Kubernetes cluster. It becomes a banking application platform. And that is the end-to-end view. In a modern bank, AKS can host digital banking services, payment platforms, onboarding journeys, fraud detection components, reporting services, integration layers, and internal applications. But every successful implementation depends on the same core principles. Design the network first. Secure identity and secrets. Separate tenants carefully. Automate deployments. Observe everything. Govern continuously. Plan for failure. Optimize cost. Keep the platform simple enough to operate, but strong enough to protect the bank. That is how banks should think about Azure Kubernetes Service. Not as containers. Not as clusters. But as a secure, governed, observable, multi-tenant platform for running the next generation of banking applications.